Professor Tai-Ping from Academic side.
Okay, it takes time. Okay, so I'm going to talk about a qualitative study for Boltzmann equation. Now, this title is a little bit unnecessary because, of course, when you started any equation, you started. No, this is okay. This is okay because I'm going to use the blackboard. Yeah. You sometimes study qualitative, sometimes study quantitative, and there's no need to mention that you are studying qualitative property. But some of you know that there's a tremendous success of the study of Boltzmann equation by the French. Well, I say French, really it's not just French, but the sort of French style, should we say, okay. And this was started in the 80s. Actually, the study of Boltzmann equation is, of course, a very, very long history. And I'm very newcomer to this thing. Although without thinking about it, it's already almost 10 years. But 10 years for me is a very short time. I've been around too long. The study before the French was actually the Kyoto school. Okay. This is a little bit interesting. To say Kyoto school, there are two schools I'm talking about. To me, really, more important school is the Kyoto School of Aeronautics. Now it's in mechanical engineering, and Professor Takata is here. This is very serious and really the most important. But I was referring to another Kyoto school, which is mathematically prominent, and that's the school of Nishida, Ukai, and so forth. So that was actually quantitative. What they do is quantitative. But the French then learned from the Kyoto school, and then there was a paper by Diperna and Leon, and they use the compactness argument, the so-called average lemma. And after that, there's a series of studies by a number of people, Bardos, Livermore, Gores, and others, eventually finish with the paper by Saint-Raymond and Gores. So what they do is to find the weak solution of the Boltzmann equation. Now the weak solution of the Boltzmann equation and is a hydrodynamic limit. So this is the Boltzmann equation. Now they call it the normalized solution, which is a kind of weak solution. Then after this study, which has lasted for about 20 years, and it basically dominate the study of Boltzmann equation on the mathematical side. And it is very fruitful. For example, Saint-Raymond and Gores could show that the weak solution of Boltzmann equation converge as this mean free path k go to 0 to the weak solution of Navier-Stokes equation in the sense of the array. Or I was wrong to say this k go to 0. You have to also have last time limit, so put a k in front of this f. Yeah, and find weakly nonlinear limit and so on. Okay, so that was a tremendous success. The Kyoto school of Nishida, Ukai, and many other people, I should say also Asano, Matsumura, and so on. There was many of them were associated with Yamaguchi sensei. And years ago, I visited Kyoto in 1983. That was in the middle of this activity by the Kyoto school. Then Yamaguchi told me that they should study the weak solution. Okay, but it's really it's not easy to say that I'm going to study strong solution, I'm going to study weak solution, I'm going to look at the quantitative, qualitative. It's very slow process. And sort of the French did that, the weak solution. You have to have different kind of habit, different kind of, I don't know, maybe different kind of food, whatever. But in any case, the French started this. And I am still going back to the Kyoto school, which actually went back to a very long history, back to Hilbert, for example. So it is a matter of habit. For me, to say that there exists a solution, I just don't see it, you know. It's there exists a solution. I need to know where is the solution, right? And how does it look like, okay? And so it's just a matter of your habit, okay? And my habit, I need to see it, right? Maybe I was grow up in a farm or something, okay? But the French, they're in the middle of this modern art, Paris and so on. They can study the existence theory. Here's the Boltzmann equation. Okay, this page is very difficult. Okay. I am still haven't get over my psychological problem with this page. This is a very difficult page. It's a Boltzmann equation I should write down on the blackboard. So what happened is that you have a function f, which is a function x and t and c. So this is the space variable, and this is the time variable. And this mysterious thing is called microscopic velocity. So therefore, it says that at the location x, at time t, how much material we have. No, this is not. So it's how much gas with that velocity. So for example, if I integrate f x t c d c over R3, say, then this would be how much material at the x t, no matter what the microscopic velocity is. And that will be our usual quantity density in classical Newtonian mechanics. Okay, so that will be the density. Now if I multiply this by f by c, that will be the microscopic velocity times the amount of the gas with that microscopic velocity. I integrate it with respect to c. So this will be the momentum. So be rho v. So this will be momentum. Again, these are all functions of x and t. So that's what the Boltzmann equation. It is monitor not just the amount of gas at the space x, time t, but also with that microscopic velocity. Now, if you do that, you may thinking about the particle system, but this Boltzmann equation is not particle system. It's mysteriously sit in between the particle system and the classical Euler-Navier-Stokes equation, the PDE. So usually people will say that this is a meso scale. Now, Boltzmann equation is a very mysterious equation, how it is related to particle system and how it is related to the fluid dynamic equation. This is one of the major open problems and still largely unsolved. Okay, so this is equation has two parts. One part is okay. Let me see. Sorry, I have a pen here. Let me get it out. So this equation, as you see up there, has two it's an equation, so it has two sides. The left-hand side is the left-hand side here tell us, this side tell us what? It's, as we know from advanced calculus, it is the directional derivative of f in the direction when you move with the microscopic velocity c. So suppose you imagine yourself as a particle and you move and you look around you how things are changing, whether there are more friends with the same velocity or less. So that is the time rate of change as you move with the particle. And if there's no collision, everybody who moves with the same speed will be with you all the time, and therefore there will be no change. However, some of your friends may find another friend and go away from you, and that's a collision. Okay, and the collision will make you have more friends or less friends. Okay, and this collision is of this form here, and this is a very difficult one. Okay, the collision operator has this complicated integral, and this complicated integral, the first thing in starting Boltzmann equation is to get over this collision operator, which one should not do. One should never get over the collision operator, because this is very mysterious. It's still largely not understood. Okay, so you have a particle with velocity c. And this is the particle you are interested in, right? Because you are monitoring how much material with that velocity. Okay, but this is one of your friends, say, okay, moving with the same velocity you do. But he may collide with another particle with a different velocity and then go away from it. And that means that you have lost a friend, okay, because you go to somewhere else. And here, when I write f, it simply is a function of c. When I write f star, it will be a function of c star, and that's the notation one you use in this Q. So you can see that there's a f and f star. So in this term, minus f star is the loss term of the amount of gas with velocity c due to collision. Okay, so that's the loss. Now, there's a loss, there's a gain. So you could have two velocity c prime, c star prime. And then after the collision, maybe better I put it here. This will become c star, and this become c. So some collision will produce a friend for you. So this will be a gain. The amount of gas here is f star prime. The amount of gas here, one is called f prime. So the gain term is f star prime times f prime. That's the gain term. Okay. And it is put here. Put here. Okay. Now the great mystery is that the amount that is gained or the amount that is lost is represented as a product. Okay, which means what? Which means that, as you know, if you have you saw a dice and you saw a coin, right? And the chance of having the head or 3 is 1/2 times 1/6. Why? Because these two actions are independent. So this is is under some assumption of independence. In this business called molecular chaos hypothesis. Okay. So this Boltzmann equation is derived under the assumption that before the collision, the gases are uncorrelated. Okay. Of course, after collision, if you go to the subway in Seoul and you say that you meet someone, you said, "Oh, okay, sorry, I'm in your way." You don't know each other. But after that, you cannot say that I don't know you other. We don't know each other. After that, you are not uncorrelated. And the mystery of Boltzmann equation is that it is assumed that every time you meet a particle, it's uncorrelated. Also, fully realizing that after meeting the particle, these two particles should be correlated. Okay, and this is a mystery which has something to do with the fact that we assume the gas was rarefied. There's something called the mean free path is fixed as the limit of number of particles to infinity. Okay, but I would not go into this thing here. Okay, if you have not suffered enough from me today, tomorrow I will talk about that. Which is very deep and a difficult thing and still largely open. All right, so the amount of the particle interact, these two particles collide, and then they come out. And how they come out has something to do with the relative position when they collide. And that relative position is called omega. Okay. Okay. So this is the fact because we assume that the particles are not sticky. They don't bump easily and then become slowed down. Okay. They bump like this. Okay. So it conserves the momentum and energy. So this says that if you conserve momentum energy, there exists omega. The collision depends on the relative position when they collide. Okay, so this is the Boltzmann equation. And this equation is one equation. Okay, but it's a very big equation because it's the derivative of x and t, and f depends on c. Okay, so it's an infinite dimensional partial differential equation. All right, so this equation has a conservation law, and that is because this Q, I did not spend enough time on that Q. And it has this picture in your mind when you think about the Q. But the Q, after collision, many things changes, right? Because when two particles collide, they change their velocity and so on. But one thing doesn't change. The total amount of particles doesn't change. Okay, two particles produce two particles. Okay, collision may change your location and so on, but does not change the total amount of particles. And therefore, when you multiply 1 times Q and integrate, it doesn't change. The action of collision does not produce a particle. It does not produce a momentum either. The total momentum changes due to the collision is 0. And the same with energy. So now you have this equation, Boltzmann equation, which is, let me write it here. So the Boltzmann equation is Ft plus Kc dot gradient xf is 1 over k. Oh, I forgot to say that this k is something called mean free path. Is the assumption that in this room there are many particles. For Boltzmann, there are infinite many particles. In spite of that, it's very rarefied, meaning that each particle will travel a certain non-zero distance before it hits another particle on average, and that is the k. Okay. So this equation, I am going to multiply it by 1 and integrate. And this will become 0, okay, because because Q does not produce the total amount of mass. And if you do that, you get the first equation. If we multiply it by Kc, the left-hand side, the right-hand side still 0, you get the second equation and the third equation. So those are the equations we call the conservation law. The first equation is conservation of mass. So let's look at this equation here a little bit, okay? So you integrate the Boltzmann equation by 1. Then the first term is called rho. So rho is by definition this one. I have to expand this a little bit. This F itself is complicated. It's the amount of gas at the x time t without velocity. When I integrate with back to all the velocity, then it's just simply the amount of gas at xt, and which is something we call density. Okay. And so rho v is the momentum. And this is energy, okay, c squared over 2 times F, this total energy. So this is what we have on this side here, okay, so we have a density, momentum, energy. But there's some quantity which is much harder to think of, like this quantity. It's called a stress tensor. This is the amount of force when you imagine your hand is inside the gas, the amount of force you experience. And the force is a vector. And if you put your hand here, this normal to your hand is the xi direction. Then the force will be Pij, J1, 2, 3. Okay, so it is a tensor, like elasticity. And this is a heat flux. The heat will go from one place to another place. This is a vector. So this equation itself, how many equations we have? 1, because rho is a scalar. Rho v is a vector. So 3 vector equation here. Energy is another equation. So this is a 5 equation. Okay, this is a 5 equation. And this is usually seen in gas dynamics. Mass, momentum, energy, there are 5 equations. However, this 5 equation is not self-contained, which means that the dependent variable, that's a density, momentum, energy. But this equation is not the equation about this variable rho, rho v, rho e. It is not. Why? Because, for example, this is straight tensor. Straight tensor, Pij, in general, is not a given function of rho, rho v, rho e. It's not. Okay. If you know rho, rho v, rho e, you in general do not know the straight tensor. But so straight tensor, of course, is very important. It's about the force, right? If you have an airplane, you want to either float, so this is lift. You don't want to have a lot of drag because this costs you a lot of gasoline. So all these are force. Okay. So if you know rho, rho v, rho e, you do not know the force in general. But how do you compute the force? Well, there's a formula here. The formula says if you know F, you know the force. So in other words, you have to know F itself. Of course, if you know F, you know everything, right? But knowing this column does not know P and Q. So therefore, this is not a partial differential equation. In spite of the fact that the Boltzmann equation only one equation, it is more than the PDE. It's infinite dimensional PDE. Okay, so this is conservation law. Then these 3 pages are the most important. If you understood these 3 pages, then you're doing pretty well. By the way, this conservation law is very easy calculus. Okay, it's integrated and add and subtract, you get this thing. Okay, there's nothing particularly difficult about this thing. And actually, Maxwell derived this before Boltzmann. But the difference is that Maxwell did not really quite believe in the Boltzmann equation. He thought, I don't know about you, when I started the square root of -1, and I never really, it took me a while to get over the square root of -1. I never feel real, you know. But it's useful. For example, you want to integrate e to the minus x squared, right? Which is the square root of pi. Using real analysis needs ingenuity, but using complex is straightforward. So therefore, some people believe in square root -1 just for that purpose, not really believe in it. This Boltzmann equation is like that. It took me forever to get over this psychological problem. I thought one should get over such a thing quickly. But later on, someone told me that Gauss one time wrote a letter to someone. He said that, oh, this is complex number. It's very funny. But maybe it is okay. Maybe order is right. Complex number is okay. Even people like Gauss, he has trouble with the square root of -1. Oh, there was a book called The Beautiful Mind, and there is a story about Nash. And Nash began to tell students, he's a terrible teacher, okay, because he thinks too deeply. And he said, square root of -1, that's called I. How about minus square root of -1, which is called minus I? But how do you differentiate I and minus I? Because both square is -1. And he began to go on with that. Okay, sorry, I'm too much digression. But I say the Boltzmann equation, the first thing you have to get over is that this is Cassie, okay? All right. Now H0. This is the really important thing that the Boltzmann did. And from here, he did create the basic statistical mechanic, that field. Okay, so the Boltzmann equation is there. If you not to multiply 1 or Cassie square, instead you multiply this by log f. Well, strictly it's not really log f, but let me just say you multiply by log f of this equation. Then what happened? Well, then the right-hand side would not be 0. It turns out that the right-hand side, after you multiply with log f and integrate, it becomes this thing here, this quantity here. This, again, is a very simple algebra, okay? Because this correlation operator is complicated, has a Cassie star, Cassie prime, Cassie star prime, but there's a transformation which make them with a Jacobian 1 -1 and so on. So if you multiply by log f, it's the same thing as multiply by log f star, or negative log f prime star, and divide by 4. Okay, this 4 I forgot about it. It's divided by 4. And the log has a beauty, as you know. Log A plus log B is log AB. Okay, I don't know about you, but this was a shock to me. How come there's something like that? So what happened is that after Boltzmann, you cannot explain why Boltzmann did this thing, because if you do that, then you can see that this guy is negative, right? Because log is an increasing function. The way I wrote it is terrible. I should have wrote this log f star minus log f prime star, right? Then you clearly is a negative number. So I asked everybody why Boltzmann, how did Boltzmann think about log? Okay, the worst answer was from Peter Last. He said that, well, you know, F log F, this information theory and so on. But that was after Boltzmann, not before Boltzmann. You know, information theory, that was a consequence of Boltzmann's greatness. Okay. The best answer was by Joe Leibowitz. He worked on statistical mechanics, and his answer was that, well, Boltzmann must have tried a lot of other functions. So, but in any case, the reason is that log A plus log B equal log AB. Okay. But the Boltzmann, I suspect that at that time, all this thermodynamic theory, they have some log somewhere there in the theory of thermodynamics. But in any case, suddenly everybody was unhappy with Boltzmann. He said that, well, Boltzmann equation was derived from the Newtonian physics. And Newtonian physics says that if this Cassini star collide into Cassini prime, Cassini star prime, then the interaction of Cassini prime and the Cassini star prime will produce Cassini and Cassini star. If this is true, this is true. This is if and only if is reversible process for particle system. In fact, in writing the correlation operator, people sometimes do this. Okay, and this is very bad. It is wrong, and was corrected by Sonnet Sensei. Say don't write this, because in case of Boltzmann equation, the molecular chaos assumption is true only before collision. So this should be erased. And this also true, and so this should be erased. Okay. But the reason when put these two pictures together in the writing of collision operator is just simply calculus, change a variable. Okay, I'm saying something about the molecular chaos assumption. But in any case, this picture people believe in when Boltzmann derived the Boltzmann equation that is a reversible process. You can change this arrow and, oh, wait a minute. Hold a second. Okay. It's better I do this. It's better I do this. Let me do it again. Okay, Cassini prime, Cassini star prime. So if you okay, that's okay. All right. So, however, now with this H theorem, suddenly the situation is different. It says that the derivative of something, the H, is less than or equal to 0, which means that this process is not reversible anymore, in spite of the fact that the Boltzmann equation was derived basically believing in the Newtonian reversible process. Okay. So, so this makes everybody to attack Boltzmann, and Boltzmann is so great that he then come up with this explanation of quantizing energy level and so on. So I was told that there are people who say that Boltzmann is the father of statistical mechanics and the grandfather of quantum mechanics, because he quantized this thing. Okay, he's my guy, so I believe anything positive about him. All right, so now, when is this 0? Well, this is 0 if f prime, f star prime equal to f star. Okay, which means that log f plus log f star equal to log f prime plus log f star prime. But you remember that we have something like this before. We have 1 plus 1 equal to 1 plus 1. This is, says that the collision does not produce a particle. It's conservation of mass. And then we have a Kc plus a Kc star equal to Kc prime plus Kc star prime. This is the principle when we do this picture. There's a conservation of momentum. And then there's conservation of energy. Square over 2 plus Kc star square over 2 equal to Kc prime square over 2 plus Kc star prime square over 2. There's a conservation of energy when we apply this Newtonian picture. All right. But now this log F also has a similar property. And Boltzmann is really a very good mathematician. He said that, he proved it zero, saying that these are the only function with that property. And log F had to be one of these. So therefore, log F had to belong to the span, the linear combination of 1 Kc and Kc square over 2. This is Boltzmann proved that. Okay. Well, if log F is a combination of this, then F will be exponential of combination of this. Okay. And therefore, Boltzmann has the first success. Namely, he recovered something that Maxwell did with a more heuristic argument, that in order for Q to be 0, F had to be Gaussian in Kc. Okay. Now, this already is a very important thing. It says that if you are in equilibrium, in thermal equilibrium, the Q is 0. When I say Q is 0, doesn't mean there's no collision. It just means the total effect of collision is 0, but it still collide. Okay. Then it had to be. But you look at this quantity here. This quantity is a function of Kc, but it's a Gaussian. Therefore, it depends only on this variable, the density, temperature, and velocity. Now, velocity is not a state variable. You do Galilean transformation, it changes. Okay. So the only state variable is the density and the temperature. Okay. You know, in thermodynamics, we learned this. There are many state variables: density, temperature, pressure, energy, entropy, enthalpy, and so on. But we are told among all these state variables, only 2 are independent. And the other things should be given function as this chosen 2. You can choose these 2 to be density and temperature, or you can choose inter-energy and pressure, whatever. Okay, but only 2 are independent. But from kinetic theory, it comes clearly only 2 are independent. If you know rho and theta, so you know F. And in previous conservation law, we know that if you know F, then you can compute every physical quantity. So which means that there are only 2 independent variables. Okay, so this is, in the case of thermodynamics, is an assumption. In the case of kinetic theory, it's a consequence. Okay. This is one example where you have to go to square root minus 1 to do integral of all this real integral. Okay. So if you go to kinetic theory, you see that this assumption on thermodynamics that only 2 state variables are independent. It's a consequence, not an action. Okay. Now let's because this quantity here is negative, and it is 0, only F is Maxwellian. So people then conjecture, well, maybe this quantity here, which is negative, this quantity, maybe it will be like it's negative, and it's 0 when F is Maxwellian. So maybe it's like that. Okay, this is not exactly true. And I heard people call this Cesariani conjecture. It's not exactly true, but basically true. Okay. So in that case, you then have what? You have something like y prime equal to minus y, right? Okay. So which means y decay to 0 exponentially. Here's a remark saying that the conservation law I have talked about is not a self-contained 5-partial differential equation because the stress tensor and the heat flux cannot be computed from mass momentum energy. However, in the case when F is Maxwellian, actually the stress tensor is a scalar, just pressure. So which means that when you put your hand in the gas, there's no shear force, only the pressure force, if F is Maxwellian. And heat flux will be 0. And the equation, conservation law, will become the order equation. All right. So now we want, let me remind you, my title of this talk is a quantitative study of Boltzmann equation. Okay, so now we try to do something quantitatively. Oh, by the way, this thing already is quantitative. If you want to quantify this thing, that is a really quantitative statement. This n equals 0 will be qualitative. So the quantitative study is hard, and therefore it has been started a long time ago with Hilbert. Okay. Hilbert, as you know, before he created Hilbert space, he was actually learning Fredholm alternative and so on, the integral equation, and also Volterra before Fredholm. So Hilbert was working on integral equation. When Boltzmann equation came about, he looked at this an integral equation. So he wanted to do something about it. All right, so here is the first effort. So you have a Maxwellian. A Maxwellian is a solution of the Boltzmann equation because if you take F to be Maxwellian, a global Maxwellian, then this is solve the Boltzmann equation. Global Maxwellian means that M is a Gaussian in C, but not a function of x and t. So this is 0, this is 0. And we just walk to see that Maxwellian make a Q 0. So it is a solution of the equation, a trivial solution equation. You say that Maxwellian is a critical state of Q. All right, so I collect all the Maxwellian here. Okay, so it's a manifold. Maxwellian, let me remind you, it depends on density, temperature, and velocity. Velocity is a vector, so 5 variable. Okay, and you collect all this Maxwellian, which depends on 5 parameters, you get a 5-dimensional manifold. Now, and on this manifold, Q is 0. I should say here. On this manifold, Q is 0 here. Right? Maxwellian make Q is 0. Q is 0 only if it's Maxwellian. Now, let's linearize around a Maxwellian, a given Maxwellian, say this one, the black one here. So I'm going to take F to be a small perturbation of M. So write F as M times 1 plus G. Then you plug into this equation and you get this equation, which we call the linearized Boltzmann equation. Now, and the linear Boltzmann equation has a linear collision operator, which is this guy. Okay, it just threw away nonlinear term. The g squared term is threw it away. You get that equation. So this is the linear collision operator. Now, of course, the collision operator comes from Q, and Q is 0 on this 5-dimensional manifold. So you can see that L is 0 on the tangent space to this 5-dimensional manifold. And you look at the computation, you have manifold, you find the tangent space, that's not so difficult. You realize that what make L0 is this tangent space, and the tangent space is the span of 1 Kc and Kc squared times m. So therefore, this 5-dimensional manifold is a kernel of this linearized collision operator. Okay. Now, I have this notation. This notation I call a fluid-like state, okay, macro state. This is MA. Excuse me. The macro state. Now, I have mentioned that if you assume the gas is Maxwellian, then the conservation law becomes the order equation. You come back to classical thermodynamics. So I will say that this is abuse of the notation. I will say that this 5-dimensional manifold is a fluid-like state. Okay. Now, if on a linear level, the fluid-like state will be this tangent space to this 5-dimensional manifold, spanned by 1 Kc squared times m. A projection onto this tangent space is called P0, which is projection onto the macro state. And the orthogonal projection is called a microscopic projection. Usually, this is not a new thing. Usually, P0 is called P, and P1 is called P perp. Okay, but Sixian, you got stuck with this one, and I got stuck with him. So, all right. So I have introduced a projection on this tangent space. Okay, and this projection is called a macro projection, fluid-like thing. That's because in fluid dynamics, really you are thinking about the equilibrium, okay, Maxwellian state nearby there. All right, so here's a Boltzmann equation, and I have a local Maxwellian. Now, for any, okay, so this is about linear level. Let me try to tie up with fluid dynamics very quickly here. So suppose instead I'm not thinking about linearization. I just have a given function f, the solution of Boltzmann equation. And out of the f, you can construct local Maxwellian. Because from f, you can find the density, momentum, straight tensor, and so on. And you can use that to construct a Maxwellian associated with f, okay, which usually make no sense. F and Maxwellian associated f is so far apart, there's no physical relevance to talk about this thing. But in some situation, one can make sense of this. So I would write f as mf plus g. So m is the local Maxwellian constructed out of f, and g is the other thing. Now the conservation law is multiplied this by the collision operator, invariant 1 Kc squared over 2. Then right hand side is 0, so right hand side is 0. When you multiply this side by 1 over Kc, then the integral of G 1 c squared over 2 of G d c is 0. Why? Because m take away all the macroscopic variable, and therefore what G is maybe still a big function, but it produces no mass energy momentum because F, this m, take away all those variable. So here's m plus G. You multiply by collision operator, G has no effect. But this term here is complicated. This F also is m plus G. If I multiply by 1 c squared over 2, this G has an effect. Okay, I'll come to that later. But if I ignore G entirely, my Boltzmann equation becomes this. The equation becomes all the equation. Okay, so you just pretend that F is m, which is never the case except in the global Maxwellian. Then you get all the equation, which I said earlier. But you can, but the real Boltzmann equation is really this one, okay? Is m plus G. Now, all the equation is the part you ignore the G. So when you multiply this conservation laws, you get more than all the equation. You still get this G somewhere there. And you can get the Navier-Stokes equation if you make a certain hypothesis. You assume that this G is there, that's true, but less than m, much less. If you say that G is much less than m, then you begin to count where are the G, where are the m. Okay, there's a G here, and there's a G here, there's m here, and so on. So on the conservation law, this G is gone, as I mentioned on the blackboard. So on the level of conservation law, only this G and this G survive because okay, I'm confusing you, but the upshot is that the G is smaller than m, the gradient of G is smaller than G, and so on. This is an assumption that made by Chapman and Enskog. If you do that, then the leading term will be this G, which is smaller than m, but has no derivative. And the leading order term is this m, which is larger than G, but with a derivative. So we equate it with this quantity. And then G, you can invert it into L inverse. And therefore, G will be a derivative of m. And you plug into this equation, there's one derivative, there are two derivatives. This becomes a viscosity term in the Navier-Stokes equation. So here's the Navier-Stokes equation at the end. I'm saying this so quickly, I apologize. But there's one way to get into the Navier-Stokes equation by assuming that it's not local Maxwellian, but a little bit away from the summer equilibrium, just a little bit away. So you admit a little bit G, but it equals the gradient of m. So this is the Chapman-Enskog expansion, and okay. So let's go back to the linear correlation operator. So the linear correlation operator, there was a result. I have this picture, which says that over this 5-dimensional manifold, Q is 0. Okay, this is M, M1, M2, a lot of Maxwellian. Now, when I linearize the Boltzmann equation, then the linear correlation operator is called L. And the Q is 0 here, therefore L is 0 on this tangent space. So this is on the kernel of L. Okay. And there's a projection P0 which is projection onto this tangent space. So Kahneman, I should say that L itself is less than or equal to 0, and this is come from the H0. It's less than or equal to 0. That's because of the H0. All right. But Kahneman says the following. He says that L is not less than 0 because L is 0 on this kernel. But if I restrict L to the orthogonal complement of its kernel, then L is negative definite. So that's what Kahneman said here. Okay. You restrict yourself to the orthogonal complement of L, then it's a negative definite. So this is a first quantitative statement of the Boltzmann equation. Okay. Something is less than 0. If it's something less than 0 means what? Means that if you are on the tangent space, then L does nothing. But it tries to go to the kernel. And go to the kernel exponentially fast. Okay, because L is less than minus nu. So you'll be thinking about what? You'll be thinking about y prime this equal to minus nu y. You'll be compared to this ODE. Okay. So this is that Kahneman proved that if you have a solution of the Boltzmann equation which is homogeneous in X, so it's not a function of X, only a function of T and C, then the solution will converge to its own Maxwellian exponentially fast. Okay. And the proof is using H theorem and then this proposition that Kahneman proved. After this, then there's a lot of work recently by Villani, Devillet, and others for the periodic in X. Okay. But the basic thing is this. So it's all come by quantifying on the linear level of the H theorem. Now, roughly speaking, when you have a space homogeneous, you go right down to this Maxwellian 5-dimensional manifold. But if it's not space homogeneous, if the function is not just C and T, it also depends on X, then you not have one Maxwellian to go to, you have several Maxwellian. So the solution is you come down, but it may hang around this 5-dimensional manifold. And as we know, the classical thermodynamic is on this manifold. And the action on this manifold is very complicated. It's what the classical mechanics try to do. Okay, the fluid dynamics try to do. So roughly speaking, there are two types of people work on Boltzmann equation. One comes from statistical mechanics. Okay, so which is like a Kahneman type of thing. And one comes from fluid dynamics. If you come from statistical mechanics, you will be more on the probabilistic kind of thinking. If you come from the fluid dynamics, the fluid dynamics is complicated. It's a long tradition. Then you worry about the nonlinearity and so on. And that is actually richer and harder subject. Okay, so this is the subject that will have a lot of future because fluid dynamics is so difficult. And then on top of that, you have the kinetic theory consideration. I would say that nobody come close to the Kyoto School of I should not say engineering physics, of mathematical scientists. And there's two books written by Sonne Sensei. It's really excellent book. But I find out that because of our general habit in mathematical community, the book really is for mathematicians mostly, I would say, because it is very precise mathematically. And yet the mathematicians have a quite bad habit, you know. We are thinking about the integration by parts too much, yeah. But I have said this to all my friends that should read the book. And when I actually read the book, you have to go it slow. But it's really excellent book. All right, so let me say that mathematician would linearize Boltzmann equation, but they take a square root of m there for some reason. Okay, it's just for convenience. Hilbert did that, and if you do that, then the collision operator become like that. Okay. Physicists will take m here, will take square root m. This is no difference. It's just a matter of convenience. Then Hilbert find out this. He did some computation. He find out that the linear collision operator has two parts. One part is just simply multiplicative operator. It's just multiply g by a function of Kc. And that's Kc. This function nu is linear in Kc for the Haas-Fourier model. And there's another Fredholm type operator, the integral operator with this kernel. This is something